The equator of the sphere. Examples of equator states superpositions. 1. Ket plus, a state that is half ket 0 and half ket 1 added together. 2. Ket minus, half ket 0 minus half ket 1. The minus gives it a different phase. It appears on the opposite side of the equator. 3. Ket 0 plus I times ket 1, all divided by square root of 2, meaning half 0, half 1, but the 1 part is rotated by 90 degrees in phase. The I gives the rotation. This places the state at yet another point on the equator. Quantum state, the ket minus state, mathematical representation. Ket minus is equal to 1 divided by the square root of 2 times ket 0, minus 1 divided by the square root of 2 times ket 1. Ket 0 and ket 1, these are the computational basis states, or eigenstates of the Z operator. They represent the classical off and on states of a bit, or the spin up and spin down states of a particle. 1 over the square root of 2 is the probability amplitude. This factor, 1 divided by the square root of 2, ensures that the state is normalized. Normalization means that the total probability of measuring either ket 0 or ket 1 is equal to 1. The probability of measuring 0 is the absolute value of 1 divided by the square root of 2 squared, which equals 1/2, meaning there is a 50% chance of getting the result 0. Probability of measuring 1 is the absolute value of minus 1 divided by the square root of 2 squared, which equals 1/2 or 50%. The minus sign, this is the crucial part. It represents a relative phase of pi radians or 180 degrees between the ket 0 component and the ket 1 component. Why these states are special? All these equator states share a key feature. They have maximum coherence, meaning their off-diagonal density matrix entries are as large as possible. They show the strongest quantum interference. They are the most quantum versions of the qubit. In plain words, superposition states on the equator contain the most quantum mixing of 0 and 1. 2. Blue arrows shrinking into the z-axis. The set of arrows all converging toward the vertical z-axis represent decay of the transverse xy components. Pure dephasing suppresses the x and y components of the qubit's block vector. The block vector shrinks horizontally. Eventually, it collapses onto the z-axis. On the block sphere, the x and y components sit around the middle of the sphere, forming a flat horizontal circle, the equator, while the z-axis runs up and down through the poles. This means coherence disappears. Superposition becomes classical. Only population probabilities remain. This is visually illustrating the decay. The value of the off-diagonal element ρ01 at time t equals its value at time 0 multiplied by e raised to the power of negative gamma times t.